Howdy and welcome back. We'll go ahead and finish this lesson by giving some examples of overloading a variety of operators, both as members and non-members for a user-defined type color that we've been building up over the past couple of lessons. So let's go ahead and start with one of the operators that must be defined as a member, and that's going to be the copy assignment operator. By default, essentially what's going to happen is the compiler will perform a memberwise copy. So if we have, say, two color objects, what it means to write C1 is equal to C2 is that essentially C1 will get the essentially the corresponding values in C2's field. So C1's R becomes whatever C2's R is. C1's G becomes whatever C2's G is. C1's B becomes whatever C2's B is. So in a lot of applications, that's that's okay. We don't need to do much more than the default implementation that the compiler provides to us. However, when we get into dynamic memory and user-defined types, we'll see that overloading this operator is actually critical. So I'm showing an example here. So let's say we do want to overload the copy assignment operator. Well, what we're going to see here is it's going to follow this structure. What's going to be returned here is going to be a reference to a color object. We'll see that in this particular application and many others will be a self-reference to the object that invoked it. I'm going to go ahead and suggest that you do not worry too much about this right now. Just understand the convention. And we'll get into where this is important, such as if we were to write things like C1 equals C2 equals C3. Then returning the self-reference becomes important because this gets evaluated first, C2 equals C3. It essentially was evaluated by this function. So if we want to then evaluate whether or not one is assigned C2, well, we better return a reference to the object on the right-hand side of that operation, which would then allow us, with the reference being returned, C1 is equal to C2. Had we said we're returning something else, or maybe a different, say, type of object, we definitely would run into some issues. But anyways, okay, that outside, a bit more detail than I wanted to go into it. That's one of the motivations for returning this self-reference. Now, the name of the operator that we're overloading, operator equals, that's suggesting that, okay, we're going to have a user-defined definition of what it means to copy one object of this type with another, or in other words, assigning, say, one color object another. The right-hand side is going to be the color object being passed by constant reference. We don't actually need to mutate whatever's presenting on the right-hand side. So let's go ahead and apply that safeguard as necessary. Like any other member function, we're going to go ahead and jump over to our corresponding source file to provide its definition. Everything else is matching up with the caveat that we have to say, hey, we're providing a definition for a member function. And we do that by saying this is colors operator equals that is being defined here and not some other one. So if we get into the body of this, I'm just running through the same implementation that the compiler does. And I'm just saying, okay, R is equal to right-hand side's R, G is equal to the right-hand side's G's value, B is equal to the right-hand side B's value. Okay, cool. Well, the question at first is, okay, well, how does it know what objects R, G, and B is being assigned to? And again, if we have something like C1 is equal to C2, remember that this is evaluating to C1.operator equals C2. Now remember, too, that guess what? C1 is passed implicitly to operator equals. And it's essentially communicating that, okay, hey, in this call, let's go ahead and resolve any member variables to the object that we invoked this operation on. So in this case, R, G, and B are all going to refer to or be looked up as C1's R, G, and B values and not some other color objects R, G, and B values. Second thing to note, hey, I thought R, G, and B were private. How the heck can you access them directly here? Well, notice that operator equals has been scoped to the color class, meaning it has access to any color object's private data, not only the one who invoked it, C1, but also the one that was passed as a parameter to it. So it has raw access to those variables, and it can go ahead and access, say, the right-hand side's R, G, and B without having to go through their accessors. Likewise, to make assignments to the left-hand side's R, G, and Bs, we don't have to go through the setters or mutators. Now, here's that last thing we kind of talked about. Okay, we're returning a self-reference. What the heck does that mean? Well, that's this statement. When C1 is passed implicitly to operator equals, there's a pointer that stores the address of C1. Okay? So what that means is when I dereference this, I get back, and we can express this as a pointer to C1. When we dereference this, we're actually getting back C1, or the object that invoked this function. And since we're returning by reference, what is going to be returned is a reference to the actual C1 object. So another way to go ahead and essentially communicate to the compiler and go, hey, I want to explicitly communicate that the copy mechanism for this user defined type is going to be just this, a memberwise copy. I can go ahead and again, that's the behavior that the compiler provides anyways. You can just say the copy assignment operator is going to be equal to the default implementation, and that would go ahead and communicate that to the reader. And it will throw kind of an additional number of problems within VS Code, because VS Code is going to go, hey, you explicitly gave a definition of the copy assignment operator. Maybe there's a couple of other operators or functions rather that you'd like to provide definitions as well to. This will clarify which ones that are, why the so-called rule of 3, rule of 5 is important when we get into dynamic memory and classes. But right now, just understand that when you're saying is equal to default, the default mechanisms are happening. And that, again, is a field-wise copy. And just to like throw this home, let's say we have C1, and I'm just going to lay it out like this. Here's R, here's G, here's B. Let's say it's 80, 0, 0. C2, let's say we write C2's R, G, and B fields is just going to be a memorized copy. So whatever's in C1's R is going to be copied into the corresponding field in C2, likewise for G, and finally likewise for B. And then the end state there is going to be, as you might presume, 80, 0, 0. And again, that's what we mean when we're saying a memberwise copy is occurring. It's just each corresponding field in the object on the left-hand side gets the values of that on the right. So the next operator that I want to go ahead and run through is going to be another compound operator plus equals. Per our guidelines, this was defined as a member function. And as such, we'll go ahead and run through it. So if we go ahead and look at the declaration, we can see here that convention of a self-reference is also sensible here. We'll see instances where it's not, so don't always assume that a self-reference is being returned. For instance, there's some cases where we'd like to return a Boolean value, for instance, the test of equality. There's others where maybe a new object in its entirety would be returned. There's a number of different scenarios, and we have to go ahead and consider that as we're defining these operators. So next up is the name of the operator. Operator followed by the symbol of that which we're providing this overload for, in this case plus equals. And then we can see here, as one might expect, binary operator, though defined as a member within our color class, we're going to have a single parameter, and it's going to be a constant reference to another color object. And remember, this is a binary operator, but when we're writing something like C1 plus equals C2, what's going to happen in this case is going to be C1 dot operator plus equals C2. So we actually only need one parameter, which is what we'll go ahead and take the single argument, in this case, C2. So, well, how the heck do we define this for color? Well, it's our own type. We can define it however the heck we want. I decided to go ahead and define what it means to plus equals one color with another as blending two colors together, which would prompt the color on the left-hand side to take on the average of the each corresponding field across the two objects. So we'd essentially proceed as follows. The new R value for C1 is going to be its previous value plus the value of that on the right-hand side. And we're going to go ahead and divide that summation by 2. And we're going to follow that similar process for G and B. And at the end, it would be kind of the equivalent of taking some maybe blue and red color paint, mixing them together. That's what we're doing here. We're essentially just creating a blend, assuming equal parts. As before, we're seeing the return of that self-reference. And again, remember that the address of the object who operator plus equal was invoked on, C1, gets passed implicitly to operator. It is stored in a pointer called this. So we can see that this would have the address of color, would point to it. So color lives out here at that address. And it has, I don't know, some fields for R, G, and B. Okay, cool. Well, if we want to get to that object, we have to dereference this. And at that point, we have our color object back. And then if we're returning a reference to that, well, essentially, we have just that, a reference to that object. And it might be confusing seeing the return of a reference. Just assume that there's kind of like a temporary reference that's being returned there, which if we did something like C1 plus equals C2 plus equals C3, this gets evaluated first. That reference to some sort of object gets returned. So we have C1 plus essentially a temporary reference, or in this case, that reference, it's just another name for C2. So that is, plus equals. So that's effectively what's going on there. So I'm going to go ahead and talk about prefix as well as postfix, I believe decrement. So if I have, say, color, C1, let's say I go ahead and write negative C1. What does this operation do? How should it be evaluated? I'll go ahead and leave that up to y'all, or I don't have an answer for it here, but just understand how we're crafting it together. We do have the ability to overload the prefix decrement operator. And then interestingly, let's go ahead and just look at this. So if I write something like std cout negative C1, whatever that does, the value that's going to be output is going to be the result of decrementing C1, okay? That's going to be different than postfix decrement. So to differentiate between prefix and postfix decrement, the postfix is going to have a single parameter of integer type. It's not going to be used. Nothing's really bound to it. It's just communicating to the compiler that this is the postfix definition. That's all it's doing. So when we look at how this is defined, and this is pretty much with anything at this would be hold when we were looking at, say, int I is equal to 7. Some of you asked, well, what's the difference between decrement I versus, prefix increment I versus I plus plus. Well, the postfix version creates first a copy of whatever value it is. So in this case, it would be the old value of I, so a copy of 7 would be made. In the case of our color object, the state of the object prior to this operation or operator being applied would be recorded. We go ahead and figure out what the heck it means to decrement a color object. I still don't know. Leave it up to you. And then we return the old state, which means if I were to write something like I plus plus, I would indeed be incremented by 1. However, what I would observe in output is just going to be 7, because what's going to be returned here is going to be the old state, though the updated state will be reflected in that variable if you were to write I. Here we'd see 8, here we'd see 9. And the same would hold for our user-defined color here. We'd go ahead and observe the old state in the expression. However, the next time we saw that variable, it would indeed have the result of this operation being applied to it. So here we are. We're going to go ahead and talk about addition. What does it mean to add one color object to another? Well, in this case, we're going to get a new object, and this is going to be our first example of a non-member helper function. So here, notice that its declaration is outside the class. Notice here, both of its arguments are passed explicitly. So if we have color C1, C2, and again, like when I'm writing it shorthand like this, assume that these colors took on some well-defined value somewhere, who knows where, but we used them before we came to this. So now we have something like C1 plus C2. Okay, that's going to call this overloaded operator. C1 will be used to initialize the first parameter. In this case, I named it LHS to communicate that this was the object occurring on the left-hand side of the plus sign. Then that on the right will be used to initialize RHS. Cool. So at this point, well, what does it mean to add two colors together? It's whatever we want it to mean. In this case, I'm going to return a new object. Notice that this is a color object. It's not a reference. It's going to be a brand new object that we're going to create here. I went ahead and named it blend, which looked a little confusing to me at first, but now let's go ahead and realize, okay, this is a color object, and let's go ahead and see what's happening. Notice here that since our definition for what it means to perform addition on two color objects is not scoped within the class, it is not a member of color, we cannot access the private data members directly. So in that case, if we'd like to return essentially the left-hand side color and the right-hand side color blended together as a new color, in this case, for blend, I'd have to do something like blend.r, or I could use a parameterized constructor. This way might just be easier for you to read at this point. And I would, in using that setter or mutator, to actually get the values to perform that blend, I have to use accessors because, again, I don't have access to the private data directly. I go ahead and add those two together. I take their average to go ahead and blend it out. And then that result is then assigned to blends R through its setter. Same process happens for G and B. And then I go ahead and return that brand new color object for the user to do something with. So let's say we want to overload the insertion operator. This is probably something that you'd like to do. You'd like to be able to go, okay, I have a color object. I do something with it. And then, I don't know, I want to look at its state. So I do something like cout C1. So the question is, okay, what does it mean to actually insert a color object into a stream? Well, we can go ahead and define that. However, we have to, for this operator, define it as a non-member. And you might be going, why? Notice what is on, let me write this a little clearer so you can actually see it. And then I'll pick back up. So here we go. Notice what's on the right-hand side. Anytime we defined an overloaded operator as a member, we had to have access to the actual definition of that type. We don't have access to update cout to add in operator that definition. It's library code. It's not ours. We don't have access to it. And even if we did, it's probably not sensible to go mucking around in it. So in that case, notice here, it can't be implemented as a member of color because a color is never going to essentially appear on the left-hand side of this if we're inserting into a stream. Now you could go ahead and mess with this to insert, say, to do other things than what you're typically used to, but I don't want to get into that right now. But it's something to consider, and it's been a previous exam question where I've asked, well, what if I want to be able to do stuff like this? So let's say we have a standard library vect, and I want to be able to insert vect values into vect by doing something like that with the insertion operator. How would you overload the operator to make that happen? That's typically, that has been in the past an exam question I'd like to ask to see whether or not students really understand what's actually going on here. And I'll let you think about that. Maybe I'll make it into a playground activity or put it on the next exam. I don't know. But anyways, the key takeaway here is I don't have access to the definition of standard library cout, so I can't define this as a member. Color is never going to occur on the left-hand side. So, you're never going to see like C1 std cout. That's just no. So our other option here is going to be to go ahead and define this overloaded operator as a non-member helper. So a couple important things here. The function is going to return a reference to a stream. And here, OStream can essentially be a file stream, standard library cout, string stream, which we haven't talked about. There's a variety of different streams that OStream kind of encompasses. The name of the operator that we're providing the overload for is going to be the insertion operator. And it's a non-member binary operator, so we'll have two arguments. The first is going to be a reference to a standard library OStream. Again, this you could use, essentially once we have this defined, it doesn't matter if we're passing a file stream to it or say cout, it'll work just fine. And the reason being is that both of those stream objects kind of derive from OStream. So they're from the same family. So you're able to pass them to this function. And I'll leave it at that till we speak about inheritance more. One important thing to realize in C++ is all OStream objects have to be passed by reference. You cannot essentially copy them. You cannot pass them by value. So this is that ampersand there is critical. If you don't have it, this won't compile. Now, the second argument, we're going to go ahead and pass by reference to const simply because, well, we probably don't want to continuously be making additional copies of color objects when the one we already have is sufficient. So color is going to be passed as a reference to const. So how do we go ahead and define what it means to insert a color object into a stream? Well, it's completely up to us. Whatever information we'd like to insert into that stream, we can go ahead and use. However, we're going to have access to that data that we'd like to insert through accessors. The reason being is that, again, this has no private access to color. It's not scoped within the colors class. So we're going to be restricted to using the accessors. You might see implementations of this where this function is declared as a friend of, say, color. We're never going to do that in this class. Do not break encapsulation and do that. Use the method that's being presented here. Anything else, I just don't do it. It won't be cool to see that if you do. Just use this. Let's use the accessors and it's not break the encapsulation that a class otherwise affords. So, okay, we have access to that data through the accessors, and we can just simply begin inserting it into a string. Notice here, how this looks is nothing like, or is everything like if you were inserting these values to a file, or if you were inserting them into, say, cout. I mean, cout etc. I mean that, and in fact, if you go ahead and write cout color, guess what that OS is bound to? Cout. So it's essentially effectively doing the exact same thing. Likewise, if it's a file stream. So yeah, we can go ahead and again, this is user defined, so it's whatever format we'd like. In this case, I'm just saying, okay, between the RG and B values, I'm putting a tab. Boom, going through, and then you have to remember to do that. If you don't, you will see another compilation error. Well, it's either going to be a compilation, it'll happen at runtime, yeah. So this will actually produce a runtime error if you're not returning a reference to that OS stream. So make sure that after inserting everything into the stream, you go ahead and return OS. Otherwise, you'll get a cryptic error while your program's running, and I'll go ahead and put you to these slides and go, hey, did you watch this lesson? So do not neglect that. Make sure you go ahead and actually return that value, or in this case, that reference. So without ado, we've ran through a couple of examples of operator overloading. I would highly encourage you to go ahead and run through this, pull out the code for this for the previous couple of lessons, work through color through these lessons, adding in the different functionality from the basic accessors and mutators from a couple lessons back to the constructors from last lesson, and then begin overloading the operators. I think going through those motions will really help you understand how you do these sorts of things in the C++ language, and will, as a whole, really help your understanding of classes in general.